And to finish off some of these ideas, let's look at some more eigenconnections. Okay, so here is one fact that has to do with eigenvalues and eigenvectors. Let's say that you have two non-zero eigenvectors and they correspond to different eigenvalues. Well, in that case, they have to be linearly independent. Okay, so if I take one eigenvector for one eigenvalue and another eigenvector for another eigenvalue, and of course I don't pick them to be zero, otherwise this couldn't possibly be true, but under those conditions, then those two vectors have to be linearly independent. Here is the simple proof. Well, so what we're saying is we're starting from two different eigenvalues. And let's say that u is an eigenvector for the eigenvalue a, and v is an eigenvector for the eigenvalue b. Okay, so we're assuming if we pick one for the other, and the two eigenvalues are different. All right, let's suppose that those two vectors, those two eigenvectors u and v, are dependent. Well, there's only two of them, so in order for them to be dependent, they have to be a multiple of each other. So let's say that u is going to be some multiple of v. Okay. But if that is true, now what happens? What happens that if we look at AU, on the one hand, AU is supposed to be equal to the matrix A times the vector U has to be equal to the number A times the vector U. But if U is equal to KV, that turns out to be equal to AKV. On the other hand, if U itself is equal to KV, then A times U is equal to A times KV. And AV is equal to BV, because V is that kind of an eigenvector for A, and therefore we end up with AU also has to be equal to K times B times V. But now we have two multiples of V which are supposed to be equal, right? AKV and KBV both have to be equal to matrix A times U. And so what that means is the only way for this to be possible is the two scalars are equal. Okay, but if I divide by K, then that implies that A is equal to B. Well, let's see where we've gotten here. We've started by assuming that A and B were not the same, and we have ended up implying or concluding that A and B are the same. Something's got to give. What's the only other thing that we assumed? Dependence. Therefore, those two cannot be dependent, have to be independent. Otherwise, we would have a contradiction. A similar eigenconnection, a similar connection among eigenvectors is more general than this, and it simply says that a set of non-zero eigenvectors, each corresponding to a different eigenvalue, had to be linearly independent. So it's not only true for two eigenvectors corresponding to two different eigenvalues, but if I pick any set of non-zero eigenvectors, as long as each one of them belongs to a different eigenvalue, they have to be linearly independent. The proof is exactly the same as before, it's just longer because we cannot rely on the fact that linear dependence means that they're multiples of each other, but it goes along the same lines. You assume that they're dependent, so there is some linear combination, and you prove that the linear combination cannot exist, and so on. The last eigenconnection I want to make is the following. If let's say that P of lambda is the characteristic polynomial of A, so remember that means that is the determinant of the matrix A minus lambda I. Well, under those conditions, then the determinant of A itself is going to be equal to the value of this characteristic polynomial at 0. The proof is very easy, much easier than the one before. Now remember once again that the characteristic polynomial is the determinant of the matrix A minus lambda I by definition, right? Okay, put lambda equals 0. What do you get? A. Okay, the determinant of A. So that's very easy. It may not look like an earth-shattering thing, but it can be something quite useful in situations where in fact the characteristic polynomial can be found one way or the other. And that's it for general ideas about these further connections among eigenvalues and eigenvectors. In class, we're going to see how they apply. We're going to check a few examples where this happens, and hopefully that's going to strengthen your understanding of these concepts.